Hi folks, Mr. Long here. We're going to do a screencast on the mean value theorem. We're going to do a little bit harder of a problem this time. I want to go over, however, what the actual formal definitions of the mean value theorem are. So two things. Initially, the function must be continuous between x equals a and x equals b, right? The function must be differentiable between x equals a and x equals b. And if those two conditions are satisfied, we can start looking at the mean value theorem. So here's what the mean value theorem is. All it says is the slope from a to b, which is this slope here, right? And this right here would be f at b. This is f at a, right? And then this is x equals a, x equals b. So what is the slope of that secant from a to b? The slope of the secant is f at b, the y value at b, minus the y value at a, all over b minus a. And what it tells us, what the mean value theorem tells us, is that there must be a location on the curve with the exact same tangent slope as that secant slope if the curve is differentiable. Okay, continuous and differentiable, but differentiability implies continuous. Okay, so that's the mean value theorem. And then when you put it all together, what you do is you say, okay, there's some derivative value at x equals c that is equal to the secant slope. And that right there, folks, is the mean value theorem definition. Tangent slope equals secant slope, but the function must be continuous and differentiable. So let's go ahead and to our example. So here is a function. G of x equals, this is a trickier one, composition of functions. G of x equals 6 minus 2 bracket x minus 4 to the 2/3. And what we're going to do is just follow some instructions here to give us some thoughts about it. What I want you to think about, let's look at what the instructions are. The instructions are to draw a secant line from 1 comma g at 1. So we've already got a little bit there. So there's 1 and g at 1. And then we want to put another dot here at 5 and g at 5. And then let's connect that with a secant line. Okay, so I can already see a problem. So yes, it's continuous. No, it's not differentiable between 1 and 5, right? So that location right there is not differentiable. Okay, not differentiable there. So if you look at your slopes, like right here, the slope right there looks to be about, I would say, 1, right? So the slopes from here to here go from 1 all the way up to positive infinity, right? Because the tangent at a cusp is vertical. Then if we look on the other side, what do the slopes go between? And this is really understanding the mean value theorem at quite a high level. So if we assume that this slope was, say, -2, I don't know, something like -2 right here. So that slope there is -2. Then what is the range in slopes? Well, the most negative number here would be negative infinity all the way to -2. So those are the possible slopes between A and B. Well, is that all possible slopes? I don't know. Let's think about it. What slopes are missing? So I've got negative infinity, positive infinity, but if you notice, there is no slope between -2 and 1, right? The slope goes from negative infinity to -2, and then from 1 to positive infinity. So f prime, the values of f prime, if I did this, I could say f prime, not x, but f prime, like the slope values, f prime would belong to negative infinity, comma, -2 union 1 comma positive infinity. So there's no slopes between -2 and 1. So that means if the secant slope here to here, if that secant slope is between -2 and 1, the mean value theorem doesn't work, right? So if we look, that's 4. Looks like that is 2. So slope of the secant is 2 over 4, 1/2. Well, 1/2 falls in between the -2 to 1. Okay, so this is going into it in quite a level of depth. Okay, so if you're struggling with this, you might want to pause and rewind it. But what we can see here, folks, is that the mean value theorem, we know it doesn't work because a point is not differentiable, right? So so that's, so if it says tell why there is no value of x equals c between 1 and 5, you would just say that there can't be a slope because it's not differentiable. So let's take a look at below what it says here. So part B. So I'm going to just redraw this graph. 1, 5. And I'm going to do like so, just show that part of the graph. Whoops, not 5. We want to focus on 4. My fault, on 4. So that's what the graph looks like. And it says now, function g does have a value x equals c in 1, 4, for which g prime at c equals the slope of the secant line from 1, g at 1 and 4, g at 4. So let's draw that. There's the secant right there. So it looks like, if I look at, so what I'm doing now is I'm only looking at the section to the left of that cusp, okay? I'm looking to the left of the cusp. So I've got a secant from 1 to 4, and then it looks like if I draw a tangent with the same slope, it's going to be right about there. So I don't know, something around 3, something around x equals 3. So here's a case where if I have an interval that includes a non-differentiable point, then the mean value theorem won't work. But if I have an interval that doesn't include it, then the mean value theorem does apply, right? It does apply. So from the graph, C looks like it's about 3. Is G differentiable on 1, 4, the open interval? Remember, that's an open interval. So that means is it differentiable at 4, but is that differentiable up to and not including 4? And yes, it is. It's just not differentiable at 4. And it's definitely continuous. So it meets the criteria for the mean value theorem. Okay, it meets the criteria. You just can't go across a point where it's not differentiable. All right, so we're going to take this question and we're going to do part B algebraically. This again is challenging. Okay, this is quite challenging. So here's our function. Our function is g of x equals 6 minus 2 bracket x minus 4 to the 2 over 3. And what we need to do is, the mean value theorem says f prime at c equals f at b minus f at a all over b minus a. Now the nice thing is, from 1 to 5 here, we've actually got, well, you know what, we can go ahead and do this. We can figure all these things out. So let's do, first thing I always do is figure out the secant slope. Okay, so what is the secant slope? And the secant part is this part here. All right, so let's go with f at b, which is, so f at b equals f at 4. In this case, right, we're doing it from 1 to 4. So f at 4 will be 6 minus, brackets, 4 minus 4 to the 2 over 3. That's just going to be 6. So that's f at b. F at a equals f at 1, which will become 6 minus 1 minus 4 to the 2 over 3. Okay, so 6 minus negative 3 to the 2 over 3. Well, what is that? Okay, what is that? And that's a bit of a tricky one. 6 minus negative 3 to the 2/3. So that's the cube root of negative 3 squared. Okay, the cube root of negative 3 squared. So we know from our diagram, which I'm going to erase now that we've used it. It looks like it's right there, so it's looking like about 1.9. I'm not going to I'm just going to approximate that. So f at A is about 1.9, something like that. And so then the slope of our secant, f at B minus f at A all over B minus A, becomes f at B, remember we just figured it out to be 6 minus 1.9 all over 4 minus 1. Okay, 6 minus 1.9 is about 4.1 over 3. Okay, slope of the secant. So it's about 4/3. So the slope of the secant is approximately 1.3 repeating. All right, 1.3 repeating. That's the slope of the secant. Now what I need to do is figure out an equation for slope of the derivative and set that equal to the slope of the secant. So let's do that. So I know that f at x is 6 minus x minus 4 to the 2 over 3. Okay, let's go back and just make sure we're right. Minus 2x minus 4. Whoa, I did make a mistake. Okay, so now we need to get f prime at x, the tangent slope. The derivative of 6 is 0. Then it's going to be minus 2. And then I have to multiply by that exponent, which is 2 over 3. And then it's x minus 4 to the 2/3 minus 1, which is negative 1/3. And that's all I have to do, because I don't really have to do the chain rule, because it's just 1x inside the brackets there, and the derivative of 1x is 1. So there's my f prime at x. So it ends up being negative 4 over 3 x minus 4 to the 1/3. Okay, and that's f prime of x. And then what we want to do is figure out where f prime at c equals slope of the secant. So what I end up with is negative 4 over 3 x minus 4 to the 1 over 3. By the way, your homework questions won't be this difficult in terms of algebra, but I figured this would be a good one for you to practice afterwards on your own. And that's going to equal 1.33 repeating. Or 1.33, you can just, 1.33 is fine. So, how are we going to solve for that? Well, I need to isolate for x minus 4 first. So the first thing I would want to do here in this situation is get that in the numerator. So I would do reciprocals. So I would have 3 bracket x minus 4 to the 1/3 all over negative 4 equals 1 over 1.33. And then I would multiply both sides by negative 4 and divide both sides by 3. X minus 4 to the 1 over 3 would equal negative 4. I'm multiplying both sides by negative 4 over 3 times by 1 over 1.33. That actually works out to negative 1, approximately. So x minus 4 to the 1/3 is negative 1. How do we solve that equation? Well, the opposite of Like, how do I get rid of 1/3 in the exponent? I multiply by 3, which means I have to cube both sides. So I'm cubing both sides. So I end up with x minus 4 equals -1 cubed, which is -1. X is then going to be -1. I have to add 4 to both sides, plus 4, and x equals 3, which is exactly what we figured out. Okay, so that tells us, what does that tell us? What did I just do? I set f prime at c equal to the slope of the secant. So, and I did f prime at x. So that means c equals 3. Therefore, at x equals 3, the slope of the secant from x in the interval x equals 1 to x equals 4, that secant slope is equal to the tangent slope at x equals 3. And it satisfies the mean value theorem. Okay, average slope equals instantaneous slope. All right, so that's a long one, I know. A lot of details in that. That one you might want to pause and go over again just to make sure you understand it. Have a good day.